Welcome to the wave model of light simulation. Today you will learn about how different surfaces reflect light and how this can affect photography. You will use this knowledge to capture outstanding wildlife in bright and sunny Antarctica. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you are playing a Labster simulation? Your first mission takes you to Antarctica, where you will meet an enthusiastic photographer who's using physics to improve their photos. I hope you're ready for your trip.
Welcome to Antarctica. I'm Nicholas and I am on a mission to capture images of the wildlife here. You arrived just in time to take the perfect photo of this penguin on the glacier. Of course, the perfect picture doesn't take itself. All the reflective snow and ice around here sure makes for a lot of white pictures. I think we might need to limit the amount of light reaching the camera. To get my perfect shot, you better go learn about light reflection and refraction while I keep an eye on this penguin. Luckily, I know just the right teacher and lab to help explain these concepts. See you back here when you know what to do.
Good, you're back. Let's not waste any time and get started with your first mission. Find the lockers and open one of them. Find a lab coat inside the lockers and put it on. Great. You look ready for lab work. Let's go to the main lab. Welcome to the lab. Why don't you take a look around? I will guide you through learning about wavelengths, reflection and refraction angles. We also have a special guest who is always contemplating light. Let me introduce you to Dr. Einstein.
Hello there. I've been collaborating with Nicholas in Antarctica on a photography project about glaciers. He has been sending me glacier samples and I've been here analyzing the physics behind glacier photography in Antarctica. I'm happy to share my knowledge with you. There were many physicists before me who studied light. Some reasoned it was a particle and some thought it was a wave. With his discovery of electromagnetic waves, James Maxwell could make accurate predictions about behaviors of light such as reflection, when light bounces off a surface, and refraction, when light bends as it goes from one medium into another, for example from air into water. However, this model could not explain all behaviors of light. Through my work on the photoelectric effect, I realized that light is in fact both a wave and a particle. Today, this is known as the wave-particle duality, and zero-mass particles of light are known as photons. The photoelectric effect is fascinating, but it is a story for another day.
Einstein started a bit of a controversy about 100 years ago when he published a paper about light's behavior. Do you know how the scientific community accepts that light behaves today? You can check the Theory tab on your lab pad if you would like to read up on the theory before answering. That's right. Since Einstein published his theory in 1905, scientists have performed experiments proving that light behaves both as a wave and a particle. Previously, light was thought to behave only as a wave traveling at a constant speed, regardless of how fast you are moving when you measure it.
I argued that light is a collection of tiny discrete particles called photons. Do you know the mass of a photon? Exactly. I called this the quantum theory of light and suggested that photons traveling at the speed of light in a vacuum have zero mass.
Dr. Einstein, photons are pretty cool, but let's not get carried away on weightless particles. In this simulation, we will focus our attention on the wave-like behavior of light. We will need to understand how we can influence the amount of light that reaches Nicholas's camera.
You are right, I'd suggest starting at the electromagnetic spectrum workbench. I'll be reflecting on light at the optical table.
Do you want to follow Einstein's suggestion and start at the electromagnetic spectrum workbench? Go to the electromagnetic spectrum workbench. The electromagnetic spectrum is a group of electromagnetic waves, ordered by their wavelength and frequency. Visible light, which we are working on today, is one type of electromagnetic radiation. Other electromagnetic waves have either longer or shorter wavelengths than visible light. Click on the computer screen to see a visual representation of an electromagnetic wave. Light waves are a type of electromagnetic wave, named because they consist of both an electric and a magnetic component which oscillate perpendicular to one another. You can see the electric component in red and the magnetic component in blue. Electromagnetic waves are defined by their frequency and wavelength. Click on the right tab on the screen to view the entire electromagnetic spectrum. You can see that visible light occupies only a small section of the electromagnetic spectrum. Humans cannot detect most wavelengths, but you can definitely detect light if you are seeing this lab room. Which of the following is a unique property of visible light? Definitely, all electromagnetic waves travel at the same speed in a vacuum despite their wide range of frequencies and wavelengths. However, because of the properties of the human eye, only light waves with wavelengths between 390 nanometers and 700 nanometers can be detected by the human eye. Cameras used for photography capture a very similar spectrum, but there are also cameras that capture the infrared or ultraviolet spectrum. Since we are interested in photography, let's focus on visible light. In Antarctica there is lots of light reflecting off all the snow and ice. To help understand this, let's go visit Einstein at the optical table. Click on the optical table.
Optical tables are very stable. This allows us to precisely play around with light. Thanks to our colleague in Antarctica, we have two types of materials to analyze today. In addition to classic mirrors, we also have glacier samples collected by Nicholas. Thick snow acts like a mirror and reflects almost 100% of the light hitting it. Meanwhile, ice in glaciers and frozen lakes refracts some light.
For today, we will optimize the intensity of light reaching a target. You will take advantage of how light reflects and refracts differently through slits containing mirrors and glacier samples. Reflection and refraction is described by Snell's law. I have put this on a poster, so you can refer to it while you do the experiment. Let's head there now to have a quick look at Snell's law before you start. When light passes from one medium into another, for example from air into water, there are two things that can happen. First, the light can be reflected, bouncing off the surface at the same angle it hit the surface. You can see this as the two angles θ on the poster. Second, the light can be refracted. Refracted light enters the second medium, but something happens to the angle. When light enters a different medium, the speed at which it travels changes. Therefore the intensity and direction of the light waves also change. On the poster, you can see that θ and θr are not the same.
Before you start, don't forget you'll be playing with lasers here. Lab safety can extend your career.
Very true. Put on the safety goggles. Let's start by placing only mirrors in the slits on the optical table. What do you predict will happen? Let's try it. Place only mirrors in the slits on the optical table. Click on the red button to turn on the laser beam. When all of the slits contain mirrors, 100% of the laser beam is reflected and reaches the target. This is very intense and would oversaturate a camera.
I have been doing some measurements on the glacier samples from Nicholas and determined that they do not behave like mirrors, but follow Snell's law. What do you predict will happen if you filled all the slit positions with glacier samples? Remember that you can lower the lab pad to look at the angles of the slits on the optical table.
Remove the mirrors and place only glacier samples in the slits of the optical table. Nice job. You can see that some of the light got refracted this time due to Snell's law. Let's see if you fully understand Snell's law now. If the angle of incidence is 40 degrees, what is the angle of reflection? Yes, I can see you reflected on this. The angle of reflection is always the same as the angle of incidence. The angle of refraction depends on the refractive index of the incident and refractive medium. The angle of refraction is calculated using the equation Ni times the sine of theta I equals Nr times the sine of theta R, shown on the lab pad. If Nr is larger than Ni, which statement is true? You can look at the poster of Snell's law before you answer. Not quite. This is a really hard question. Please try again, and remember you can check out the poster of Snell's law in the theory pages. You really are enlightened. The equation Ni times the sine of theta I equals Nr times the sine of theta R states that the refractive index of the first medium times the sine of the angle of incidence is equal to the refractive index of the second medium times the sine of the angle of refraction of the second medium. If the refractive index of the second medium is larger, it follows mathematically that the angle, and therefore the sine of the angle, will be smaller. You will see this as the refracted ray bending towards the normal.
Wow, you are learning fast. As a photographer in Antarctica, you should always try to optimize the intensity of light that reaches your camera. Understanding the light intensity will help you select your camera's exposure settings, but as a photographer I bet you know more on this topic than a physicist like me. Nicholas has been following your progress and is waiting eagerly for your results.
Before you go, how can you compensate for the high-intensity light that's present snowy and icy Antarctica while photographing the penguin? Good thinking. We are trying to limit the amount of light that reaches the camera's sensors. The amount of time the shutter is open and the size of the opening through which the light enters the camera affect how much light you see on the finished photo. You could also try taking the shot from a different angle so the light is not reflected directly into the camera, or find an area with fewer reflective surfaces. Perhaps there are some rocky patches near the penguin?
Excellent job on understanding reflection and refraction. While you've been gone, I have optimized the exposure and aperture settings to reduce the amount of light that goes into my camera. In my last mission photographing low-light caves, I had to do the opposite. I'm glad the penguin is still here. What a coincidence, it seems like it hasn't moved at all. Wow, nice photo. I see you learned well from our expert colleagues. I would say you are ready to begin a fantastic career as a wildlife photographer here in Antarctica. Now, let's go. I saw some seals on the rocks over there.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.